So what are assertions, right? So assertions are primarily, they are trying to capture the behavior of a system, right? And when we say behavior, behavior in the form of waveforms, this is a very important point, right? And this waveform could be like, it could be an individual signal timing, or it could be timing with relationships to the other signals, right? So both of them can be captured in the form of assertion, right? And then once the behavior of the system in terms of its signal behavior is captured concisely and completely, then you use that captured behavior for different purposes. So one purpose is that you can check that one you have now captured a behavior, and then you can that captured behavior can be checked that whether it is in compliance with the specification or the requirements, right? So that's our one of the primary purpose of our verification. Or second, it can be used to cover that particular, whether that specific behavior has it taken place or not, we can cover it as a functional coverage, right? So functional coverage can also be obtained through the assertion coverage, so that is also possible. And third is that it can be used by formal tools primarily to create the waveform that you have specified. So the tools can generate the waveform and prove that your design is going to behave as per the requirements that you have captured. So those are the three purposes for which the assertions can be utilized. So one point that I want you to keep in mind, as I have said, the assertions is all about waveforms, right? So you have signal, you have events, as we indicated. Then there could be a relationship between the events. There is a repetition that is possible, and then some after one pattern, other pattern happening. Both of them going low. There can be different types of patterns, and assertions is all about capturing these type of signal information in a more concise way. That is the point I want you guys to keep it in mind, and this is a very important point to hold, and this helps you figure out where we can apply assertions and where we cannot. So for example, now I can ask myself a question that since the SystemVerilog provides this construct called assertion, can all the checks in test bench, can I implement only using assertions, right? So that's a question I can ask myself. The theoretical answer for that is yes, maybe you can, right? But the practical answer is no, right? It's not possible. And because assertions have its own strength areas and it has its own weak areas, and when you try if you try to implement everything through assertions, then you would be venturing into its weak areas as well. And when you try to do something in its weak areas, then the overall effort involved in being able to do that will become very tricky. Now what happens, let's understand that a little bit as to where we can use it, where it's hard to use it, or where the effectiveness is low. So assertions are primarily used for your interface level protocol. So what do I mean by that is, like for example, we had done a the FIFO interface, right? So we have the interface level protocol over there is that, yeah, you need to, at every clock, if the full is not asserted, then only you can assert the write and send out the data. Right now, that's the interface level protocol that needs to be followed. Now if you want to do such checks at interface level, we can use the assertion, because that interface level protocol is all happening at the signal level, and hence we can utilize the assertion for that. Or if you have some microarchitecture that you have built and you want to do microarchitecture level functional checks, these are sort of a white box checks, because we are now looking into how a particular design has been implemented, and in order to do these checks also we can use the assertions, because again we are dealing in terms of waveforms when we are going inside the design, right? So when we have these type of requirements, the assertions are very effective in being able to deal with it. But if I have to implement an end-to-end check, right, now what happens is, if I have to implement an end-to-end check, then building that using assertion becomes very complicated. Okay, why that becomes complicated is that, as we know, we need a reference model to check the correctness of a design. All right. And in order to use assertions, we have to talk the language of waveforms. This is very important, right? I can't talk a high level, a transaction level, language with the assertion. With assertion, I have to always talk low level signal information, that okay, particular signal got asserted, it stayed high for so many clock cycles, and then a next signal came in. So I have to always talk a signal level language if I need to implement it in the form of assertion. I can't do a behavioral type of a talk that okay, these many transactions are stored and then is an out of order execution, and I want to look at it, and then I want to store them in some queues and arrays and then use them for processing. That type of a language cannot be effectively spoken with the assertions. And hence what happens is, now if I want to implement a end-to-end check using assertion, now I have two options. Either I rely on my design itself, which is in principle incorrect, because when I am trying to do end-to-end check, I cannot rely on the design itself to do the check on itself, because if something is wrong in the design, then my assertions are also going to be incorrect. So I need to build now a reference model of a design, and that reference model of a design that I build has to look like an HDL, right? Not like an HVL model. It's not a high level behavioral model, but rather it has to be like a low level, which is very similar to in the form of your real design. And that becomes like, it is more complex, because now you are modeling a much more level of details of a design than you really need, and the more you model, the more code you write, the more buggy it can become, and hence sort of it defies the overall purpose of building the reference model, wherein you want the reference model to be relatively simpler compared to a design, so that the correctness can be ensured to an extent by construction, or it can be easily maintained and verified. The reference model itself can be easily maintained and verified, because it's smaller in size and it's a behavioral level rather than the detailed signal level. So that is where if you want to do end-to-end checks, supporting your assertions with the additional auxiliary logic becomes expensive. So that is where you typically tend to use the behavioral models, and you do behavioral checks rather than using the assertions. And in a typical, in my experience, in the typical your simulation, dynamic simulation based verifications, about 70% of checks are generally you implement it in the form of behavioral. Like for example, your scoreboard, the way we implemented in the FIFO, it's not an assertion based scoreboard. Of course, for FIFO we could have implemented assertion based scoreboard as well, but we generally, for any complicated design, you implement a behavioral model, and only about 30%, which I talked about, either at a signal level protocol, or if you are really implementing some microarchitecture level checks, then you utilize the assertions. So in the role of assertions in the dynamic simulation is slightly limited, but assertions are very extensively used in the formal or the static verification, and this is the area that is growing. So if you master assertion, then potentially you have the advantage that you can get into formal verification as well. So that is a one reason why you should pay attention, and although it's hard area to master, still it's worth mastering, not because it's completely going to be very useful. I mean, to the level of effort that you are going to put in, and the level of value that you can extract in dynamic simulation based verification is limited, but it provides a bridge to formal verification, and hence you can say it's more valuable. And also assertion is a sort of brain teaser, so it will make you sharp. So that's another reason why you want to invest in learning assertions. Hey, before we jump into the details of assertions, what we will do is first we'll establish what does it mean to learn assertion, and what are the things that are involved, and how is it sort of like, what are the building blocks of it, and we will establish that scope, and then we will jump into the types of assertions and how do they work. So the lowest level of your assertion is Boolean expression, right? And I want to repeat over here, as we talked about, assertions is all about waveforms, right? And waveforms, as you know, have these transitions from one value to another value, right? And how do you qualify those particular values, right? That you qualify it using the Boolean expression, that is whether the signal has become 1 or 0 like a constant, or you want to do some arithmetic operations, some bitwise and or you want to do some logical operation saying that address equal to something and enable equal to 1, so something like that, right? So you are doing various you are creating Boolean expression to specify the values of some condition at some point of time, right? At a particular point of time, some condition you are trying to define, and that definition is your Boolean expression. So that's the first thing. So you look at a waveform and you put your cursor in the waveform, and at that particular point of time, a set of signals having set of values combined through some Boolean operators defines certain conditions, right? So that is the first step, that you are defining some sort of a Boolean expression or a condition. The second step is that you not only want to capture it at one point of time, but throughout some duration you want to define how the waveform is going to get created, because now waveform is going to be series of such Boolean conditions. So that's where your timing expression comes into picture. So the timing expression is also called temporal expression. So we have to, and that is something that we define using a construct called sequence. Okay, so there is a construct in the SystemVerilog that is provided as called sequence, where you define the sequence of Boolean expressions, right? So a Boolean expression defines a condition at a given point of time, and then the sequence allows you to combine such Boolean expressions to define them over a period of time, right? And then there are various operators that are provided to combine these Boolean expressions to define a timing waveform. It could be delays. That, I mean, here is something where you can see that these are all operators that when you look at it, these are attributes of a waveform, right? So delay is an attribute of a waveform. Repetition, as we talked about, how many times, like how many clock cycles a particular signal is asserted, or like let's say I have asserted for one clock cycle and deasserted for another clock cycle, and that type of pulsing happening for n number of times. So that is also a repetition within, like let's say one particular waveform is contained within another waveform, or a one particular Boolean expression is contained within another Boolean expression over a period of time, intersect, and some signal is asserted throughout the duration, right? And then the composition of these timing expressions, right? So first level, you are able to create a timing expression by which you are defining an waveform by taking different Boolean conditions. And once you have defined the waveform, now at waveform level, you can do further composition by saying, okay, this and this waveform should happen together. So I have defined two waveforms, and I can now say and of these two waveforms should happen as a part of sequence, or of two waveforms needs to happen as a sequence. And then there are operators like called as first match, wherein you have a different types of conditions taking place, and then you want to wait for the first match of certain condition, and thereon I want to match certain sequence, right? So this way sequence allows you to combine Boolean expressions to define a waveform. Okay, so this is very important point. Now that is the second layer. So third layer is the validity of these timing expressions, right? So I have defined a waveform, and now I want to tell when will this waveform become valid, right? I can say, okay, until certain point, or eventually it will become valid, or always this must hold, right? And there is abort type of conditions. And I can use also the conditional timing expressions, like I can do negation, that I can define it in a certain way, and I can say it should be inverse of that particular way I have defined. And there is a concept called implication. Implication and if else are in a way similar, where I can say if certain condition has taken place, that is if one type of waveform has happened, then I should check another type of waveform has happened, right? That I can do. Or I can say case, based on a particular condition, if the condition is of a certain value, the waveform should be of one type. If a condition is of another value, the waveform should be of another type, right? I can do, or I can disable while the reset is asserted. I don't want to do any checks, or I don't want to do any coverage on certain waveform that I have defined, because the system is being reset, so I can disable. So I can do that as a part of your validity of timing expression checking. So in summary, as a part, as we talked about, the assertions are nothing but concise representation of your waveforms, and then once you have represented the waveforms, you want to either check, cover, or give it to the static tool for generation and theorem proving, right? Those are the three purpose. So you, at the lowest level, you have Boolean expression, that is, if I put a cursor at a specific point in a waveform, what is the condition that is taking place, right? That condition I can create using constants, your arithmetic, bitwise, logical, any operator I can use, and I can create a Boolean condition. Then in the timing expressions, what I do is I create several of these Boolean expression. I combine several of these Boolean expressions with the timing operators like delays, repetitions, within, throughout. You can, the name itself gives you some level of an idea that it is defining some sort of a timing characteristics of the signal. And then once I have defined the waveforms, I can compose those waveforms to create even more complicated waveforms, saying this waveform and this waveform, they should happen together, or this waveform can happen, or this waveform can happen. I can do or. So I am able to do now the composition of the waveforms. Now once I have defined the waveforms using the timing expression, the third part of your assertion is that you can define validity, that when exactly is this waveform going to happen. Will it happen eventually, will it happen always, or will it happen after a certain condition, or should this be disabled at a certain particular point of time. So you give the validity to the waveform that you have defined. So, and that is what is which happens as a part of the constructs that are provided to which help you define the validity right now. So this is the base concept that is present when you deal with the assertion, and it's very important for you to understand this concept. If it is not clear, you listen to it again and make sure that this is clear, because on this now everything will be built further. So we looked at what are the primary or the base contents of your SystemVerilog assertions, right? The primary things are, you have the Boolean expressions, remember that very clearly. Then you have the the timing expressions, that you create series of Boolean expression and you define a waveform. And then third, you use constructs, right? So the timing expressions are predominantly defined using your sequence. Then you define the validity to the sequence using the properties, right? In the properties you define validity, that when is this waveform going to be true, right? Whether it's going to be after this condition, eventually, always, when is it going to be true, right? So that is what you're talking in the context of property. So this is the base set of constructs that you require. Now second is, there are set of accessories, you can call it, which you require to make this set of base constructs, that is your Boolean expressions, sequence, which is timing expressions, the properties, which is validity of your timing expressions. You have these three things. Now you want to have some accessories along with this. This is like your base car model, and then you have to accessorize it, right? So it's similar to this. So the accessories in case of SVA, right? As we said, this is your base. Now what are the accessories? This can be like a clocking, and I can check. So all the assertions have some sort of a clocking event, and the clocking event need not really be a clock. It could be any signal, and the events on that particular signals are used as a reference to sample the Boolean expressions that you define. So there you can do either a single clock, or you can also use multiple clocks in assertions. So both you can do. And then you can create a set of local variables within the sequences. That is, generally we talked about that at some interface level we are using the signal to do the checks. So those signal values you can sample, retain it, and use it for something else. So you can define local variables within the sequence, right? And then there is a recursions that is supported, and then there are sample value functions. Sample value functions means that you can do bit of a time travel, that you can say $past of something and get the value like 1 or n sampling clock before with respect to your current sampling point, you can either go 1 to n cycles behind and get the value, right? And of course we briefly talked about disabling. And then you can define, when you're defining the timing expressions, like for example, if I have to say a particular request has been asserted and a grant is going to come, will it come within 3 clock cycles, which is a finite length, or I can say it will come by the end of simulation, right? It is infinite. Whenever the end of simulation may be, it will come by the end of the simulation. So I can define an infinite length timing expressions. And then with respect to assertions, there is a concept of threads that will come into picture. We will look into it when we go more deeper into the concurrent assertions. So what happens is, I have defined a single concurrent assertion, and that single concurrent assertion, how many times it is going to get invoked, right? And at any given point of time, will it be active with only one instance, or will it be active in multiple instances? So that is something that there are challenges, and there are nuances associated with that. So that is your that understanding is, sort of like accessorizing yourself, right? And then we can also pass arguments. The way we pass arguments to your tasks and functions, we can pass arguments to both the sequences which help you define timing expressions, as well as to the properties which help you provide the validity to the timing expressions that you have defined in the sequence. So you can pass arguments and use it, right? So these are the various additional auxiliary things that you need to know apart from the base set to understand the assertions to the next level. So this is the second level. So you took a car model which was a base, and then you accessorized it, and once you have accessorized it, now it is ready to use, right? So now how you can use it, maybe you are using it for self-driving, or you are renting the car to someone who can take it and pay you some money, or third, maybe your friend or your some relative is driving it. So there are different now usages, right? So I had taken my base SVA set, which was made up of Boolean expressions, then series of Boolean expressions to define waveforms, and then using sequence construct, and then using a property construct to define the validity to the waveform that I had defined, and then I accessorized it. Accessorized it is like dealing with real life situations, single clock, multi-clock, and then whatever the threads channels, the thread challenges, or I use a local variable construct. I passed certain parameters to make my sequence and property reusable. All that things I have done. Now this is ready, right? So my full thing is ready. Now how can I use this, right? So I can use this in multiple ways, right? So I still need few more things so that I can package it and use it, right? So what are those? One is, I have to put an assert on that property. If I want to do the check, I have to put a cover. These are called directives. I have to put a cover on the property to cover that particular thing, or I can use it for generating the various waveforms in the formal type of a setup, right? So that is one way of utilizing these things and packaging. And second, as we talked about, that assertions cannot do everything on their own. Sometimes we might have to provide glue logic, which is an additional auxiliary logic that you might have to write, and the information of which it uses, and then you are able to write the assertions on the top of it, right? So you have to write that glue logic, and then put that all the things into one package, right? So those packages unit can be like, there is a construct called checker that has been introduced. You can put everything in that. Checker is sort of equivalent to a module, but a module where you can place assertion. So for all practical purpose, you can think of it like that, or you can put it in the module itself, or you can put it in your interface construct, or you can put it in your program construct. So in any one of these constructs, you can put all these declarations and their directives, that how you use it, whether you are checking, whether you are covering, whether you're using for generating waveforms, all of it, along with that auxiliary logic, you can put it in these units, either a checker, module, interface, or a program. You can put it in, and once you put it in, next what happens, you hook it up and then start running your tests, and things might fail. Then you need to know some ways how to debug those assertions, And if you are using the assertions means if you are using those properties for coverage, then you need to know how to look at the coverage reports. And as we talked about, there are a lot of nuances and best practices that you need to learning, gochas and best practices that you need to keep learning. So this is the sort of the third phase, where then you are now at this point you are able to not only write it and accessorize it with all, accessorize it by using various additional features, then putting it together in a nice package and then putting it in the environment, simulate it, debug it, and get the full value out of it, right? So these are the three phases that you need to look into. These are the three phases in which you need to look at learning the full SystemVerilog assertions. So just to quickly summarize it, we looked at the base where Boolean expressions were combined into timing waveforms using sequence, the validity to those timing waveforms using the properties. That is the first level. Second level, how do you kind of implement single clock, multi-clock, local variables, and the different sampling functions. So all the additional things that help you make the writing of assertion in the implementation, and they provide you some sort of utility, additional utility beyond your base. So that's your accessories. Third, you combine it with one of the directives, that whether you want to assert, cover, or you want it to use it for generating waveforms. And then where do you keep all these things, that is your properties, and then the directives of the properties. You can keep it either in checker, module, or interface, or in a program block. And then once you have placed it and start running it, how do you debug it and how do you look at the coverage reports, then learning about various best known practices and the issues that are involved. So those are the three layers in which you need to look at whenever we are learning through the process of SystemVerilog. You need to kind of identify where is this particular construct or feature that we are talking is coming about, and how do you need to learn all these things, and how do you need to utilize it better, is how you need to look at it. So one final view, or like the final summary before we jump into the real details. So at the bottom of your pyramid, which is far wider, you are going to really use Boolean expressions, which will finally result in true or false, right? And then specification of sequence of events using Boolean expressions, right? The series of Boolean expressions you are combining with the timing operators, and that is where you are defining the sequences. The third, the validity of the sequences, the behavior of sequences that you are capturing in the properties, right? The properties are going to give the validity, right? And third, just defining a property will not do anything, right? As if like we just defining a class is not going to do anything, we have to instance it. Similarly, just defining a property is not going to do anything, we have to combine it with one of the directives. It could be either assert, cover, or assume. It needs to be combined with the directives, and once you combine it with the directives, then you need to put all of these into one of the units to deploy it, right? That's your final packaging. You can put it in checker, module, package, or interface, right? So once you do that, then your complete assertion model is ready to be used. So how you should go about mastering these, right? So you probably have to do 2 passes minimum through, in order to learn assertions. Minimum 2 passes are required, right? 2 times you have to look through the details to kind of get the understanding. And third is that assertions is one area that it's going to take a long time for you to learn all the nuances. It's a very long process. And how it's going to work is that as you keep practicing, you will keep discovering certain issues and challenges and gochas. Those will keep coming up, and you have to find out how to overcome it, right? So that is a ongoing process that you will have to do it for a long time. So in the first pass, what you should do is, for each of the construct, right, like for example, there's an implication operator, there's a delay operator, there is a replication operator. The first thing is, whenever I say this operator, it should come in your mind. Am I talking about sequence? Am I talking about a Boolean expression, or am I talking about a property? That type of first level, you need to be able to segregate among these 3 layers, right? So whenever somebody says anything, are they talking about Boolean? They may not explicitly say it, but you need to build that understanding in your mind. Are they talking about a condition? Are they talking about a timing expression definition in sequence, or are they talking about the validity using the properties, right? So that point you need to keep it in mind. And one confusing point that will eventually come very soon is that whatever you do in sequence for a timing expression creation can also be done in property. Okay, so property is a sort of superset. Okay, property contains sequences, so a property can be, so you can say that a complex property can be defined, and that complex property can be broken up into smaller sequences. That's the way it works. So anything that you put in sequence can also be put into the property. So this point will come very soon. But anyway, coming back to our original as to how the learning curve will be, in the first pass for each of the operator, as we're talking about, it could be implication, it could be a repetition. For each one of them, you should try to write a small examples by yourself and generate the waveforms on the input signal of your assertion, and notice how the assertion is behaving. Like for example, when does an assertion start, when does an assertion end, there can be multiple conditions under which it passes, there can be multiple conditions under which it can fail. So you should try to think of and try to create, at least initially you need to create multiple pass condition and multiple fail condition to understand how it is behaving. At least for few basic constructs, especially like a delay construct is very important, repetition construct is very important, first match construct is very important. So for these basic constructs you should create like a different type of input conditions, and then you should look at whether it is the response that it is giving out is as expected or not, and make sure it becomes clear in your mind. Okay, even very basic sequences that we define in assertion, they can be very confusing when you start off with. Okay, so you need to do that and see. So first level, take each of them, write some small examples by yourself and look at it. Of course, I'm going to show you various examples as a part of this course, but nothing like you doing those examples again by yourself and seeing it. That's very important. Second is you go to the accessorizing, and like some level of accessorizing you'll have to do, but what I'm talking about is the advanced level that you you will probably do it over a period of time, but the some level of accessorizing you do it, like let's say you start off with single clocking, you don't really use local variables, just put it in a module and use it. That's what I'm talking about. So use it for a small project, like for example whatever the counter project that we have done and the FIFO project we have done, we have not used assertions a lot in those cases because this is an area by itself, so we have left it. So what we will do is we'll put the assertions part of those projects back into the same code, so you can use that for a simple real life project and look at it. That's the second level, right? Use it for that small project and make sure that you got it. So individual construct you are tested independent of any project, and then you are putting everything together and putting it into that particular project and see how it is working. So that is the second level, right? And third level is the nuances that I talked about, that there are going to be cases where it's not going to behave as you expected it that it is going to behave, and then you will keep discovering various tricks and workarounds that it exists, is a part of it. Okay, since now somebody could ask that, why do I need to worry about like tricks and workarounds? Because it's so widely deployed and so widely useful that there is you tolerate some level of difficulties, right? So that is why you will, because so many people are using it and in so many projects it is deployed, so we cannot complain about it. So rather what you do is you figure out how to overcome those nuances, and then those are some things that I am not going to be teaching you all of them. That is something, it's a learning process that you will have to discover as you progress in your career journey.